Okay, so we talked a little bit about the limitations of resolution last time. There's a closely related question, which is whether we're solving the right equations. And so that will be most of what I talk about. This lecture will be about thinking about the equations and what I call reduced models, or what a lot of people call reduced models, which are more suited to a particular set of scales. And then tomorrow we're going to talk about parameterizations, which is the other side of changing our equations in a way to bring phenomena that are not resolved in an approximate way. Okay, so don't we already know the equations of fluid motion? We do. Here they are. All the contributions that you need to build a complete set. But we don't know how to solve them. So that scaling of model resolution that I showed you, here's that same set of simulations and the two fit lines, or just the one fit line to the median. And now I've zoomed out to give us more of a historical perspective. So the Euler equations are back here in the 1700s, the Laplace tidal equations, the equations we need to do a rotating planet version, are over here in the late 1700s. The Navier-Stokes equations, giving us the viscosity form, come in the early 1800s. The very first weather forecast using Quasi-geostrophic model from Charney and von Neumann came here in the 1960s, I guess, 50s, 60s. And here are the IPCC models. Here is when we'll get to use the equations these guys back here invented to directly simulate the Earth with the fluid equations. Okay, so 2200. What are we going to do from now until then? We obviously are not using those equations. We're using some other equation set. So that's where a reduced model comes into play. A reduced model of the quasi-geostrophic system is one example, but I'm going to talk about even the Boussinesq approximation as a reduced model today, and then the wave average equations as another reduced model. And the other piece we need is parameterizations. So you might say that there's a new school after Fourier and Fick and all of those folks who are developing either reduced models of various flavors or parameterizations of various flavors. And I won't say this is a comprehensive list. This is more my favorites from this list. And one thing of major note is to notice how often McWilliams appears on this set of things. Okay. Okay, so here they are anyway. These are the equations of fluid motion, which come from this beautiful book by Peter Müller called The Equations of Oceanography or something like that, which, if you don't have it, is a really good thing to buy. He's just retired recently, so we can give him a retirement present of all of the book royalties of everyone buying a copy of his book. It goes through both the traditional approaches to fluid dynamics and then some of the approximations to get us to our modern framework. He doesn't solve any of the equations or even present many solutions. He shows a little bit of the wave effects, but he doesn't do much else beyond that. But he nicely sets out everything in equations that are easy for all of us to understand. Okay. So, do these look familiar? Sort of. Okay. Continuity. And I still have the divergence in here. This is compressible fluid dynamics at this stage. Momentum equation, three-dimensional momentum. There's a stress tensor, which has both the pressure as the trace of that tensor and the deviatoric stress tensor, which is where viscosity comes in. This MOL means molecular. There's the Coriolis force. And then there's the geopotential, which includes the centrifugal force, but also gravity and also tides. Okay, all of this is fine. The temperature equation. So this is in situ temperature, which has molecular fluxes. There's radiation, like sunlight, coming in, warming up stuff. There is the heat from friction. When you dissipate velocity, you actually generate heat. That's this term. And then there's this crazy one over here, the mixing heat, which is when you mix salinity, you actually heat the water. Okay, these are complicated, but they're all there in the full equations of motion. Then there's a salinity equation, which is just a molecular diffusion of salinity and advection. And then there's the equation of state. Okay. So there are a few things that are worth pointing out. One, this crazy term we never worry about. This crazy term we never worry about. Does anybody know how we get rid of those two? Maybe this one is more familiar. What kind of temperature is purely advected and doesn't have compression effect? Potential temperature, conservative temperature. So there's a lot of work on the thermodynamics of the ocean to get this term absorbed into this guy. That's fine. The problem is it actually screws with all these guys over here and makes them harder to calculate. That's one problem, because the much celebrated, this system is closed. We actually know specifically how to formulate the molecular stress tensor, the molecular heat flux, and the molecular salt flux in terms of measurable quantities. So we know all of these diffusivities. We know this viscosity. We know everything about the system for seawater. So what's the problem then with this system? How big can I make my model grid if I use these diffusivities? Tiny. So with this equation and the biggest computers we have, we can solve approaching 1 cubic meter of seawater. So that's what we got. Our ocean is only 1 cubic meter in dimension. That's not going to solve any coastal oceanography problems or even global climate problems. So, all right. So the way that I think of it, so these guys can only be used for about 1 cubic meter in size. And present computing on a reasonable sized cluster, we can take a 1024 X modes, 1024 Y modes, 1024 Z modes, and 1024 time steps, or shuffle them if you have more interest in one or the other. That's about a kilo, mega, giga, teragrid of data that we can move around, of simulation data. So we get to choose where our teragrid sits in space and time. But that's, which one do we choose? One of the things for this set of equations, which is this guy, comes from that guy, is sound waves are going to kill us in this equation. Because the CFL, Courant-Friedrichs-Levy condition, is limited by a 1,400 meter per second sound speed. That's the leading wave, the wave mode from that equation set. So, and here's how you derive it. You take the equation of continuity with the compressibility effect. You do some thermodynamics to convert from density to pressure. You then have this equation, which is the equivalent of that one, except with pressure in place of density. You combine that with the momentum equation, and you look for a linear combination of those, and you find a pressure wave equation, which equals weird things like Coriolis force on sound waves and diffusion. So we can ignore this side of it, but that's a wave equation with a 1,400 meter per second propagation speed. So now I said, does anybody know what we do with this term to get rid of that? Does anybody know now? Closer. Okay, we use the first reduced model, which is the Boussinesq approximation, which goes back to 1897. And we say, suppose, since the ocean is nearly incompressible, suppose the variations in density are small compared to the background density. And that tells us that instead of a compressible fluid, we have an incompressible fluid as a good approximation. The rest of the equations go almost undisturbed, except you get the background density appearing in places where we had the full density. So that makes our lives easier, because now this term has just been made linear instead of nonlinear. This term is linear instead of nonlinear. And you get a buoyancy as the only place where the variations, so it's the vertical momentum equation, the only place where the variations in density come back into play in the dynamics. So since in that derivation I just showed, this guy was the key in linking pressure equation to the momentum equation and getting that. If we cut that linkage between the left side and right side of that equation, we've eliminated sound waves from the system. And so if you look for this, the fastest waves now are things like surface gravity waves. And so that means that we only need to deal with something that travels 10 meters a second, not 1,400 meters a second as our limiter on the simulations. So that's great. We can go 100 times faster in terms of time steps without blowing up the model. But we lose some things when we do that. Along with losing sound waves, we lose the ability to convert internal energy to mechanical, so the ocean can't behave like a heat engine. And some of you may have heard about this being an issue in what drives the meridional overturning circulation. There's a kind of interesting theoretical debate about it, but essentially once you go to Boussinesq equations, that's gone. We also lose the ability to directly simulate sea level rise, because now our models are going to be conserving volume, not mass. And when ice caps melt, they put mass of water in the ocean, not volume of water in the ocean. When the ocean expands because of warming, it expands in volume, not in mass. And so this now becomes a more difficult detective job to figure out what our simulations infer about sea level rise, because we can't directly simulate it once we made the Boussinesq approximation. We could address these to some extent by taking an intermediate step, but that makes our equations more complicated, harder to solve, less efficient. So we tend to use Boussinesq models anyway. Okay, so before I go into this, so that's an example. Yep.
You can be compressible and still be non-Boussinesq at the same time. I mean, shallow water equations, for example.
Yeah, so that's one of the intermediate steps. So there are ways that you can do intermediate steps. You still have to filter the sound wave somehow, and you can do it numerically. You can do it. So, I mean, this is not the only solution. I'm just telling you that this is the common solution. So this, and informally, a Boussinesq approximation is a reduced model. Okay? I'm trying to give you an example of a reduced model that hopefully you've seen before, so because that was a fast introduction if not. Okay. So how would we derive more reduced models? Maybe we want a reduced model that's specific to the submesoscale so that we can make dynamics that were oriented for simulating that fast or specific to the mesoscale. Here are those same equations of motion written now in a dimensionless form where I've pulled out the Rossby number. So all of these V's are now the dimensionless velocities based on some horizontal velocity scale. This is the vertical momentum equation based on some vertical velocity scale. Now we get the Froude number and the aspect ratio out front, the Reynolds number in front of the friction term, the Peclet number in front of diffusion terms, and then this funny thing, which is, where is it even hiding? Oh, it's hiding inside of epsilon, which is over here. So this is an elaborate thing. This is an elaborate non-dimensionalization, but the advantage of this one is this spans the whole range of ocean motions from stratified turbulence through the mesoscale with just this one dimensionalization. Okay? And there's a beautiful paper by Jen McWilliams. It's 2 pages long, which lays this out. And so that's well worth checking out. But let's talk a little bit about what this means. Okay? So, and also I want to mention one more thing. So I have non-dimensionalized based on the grid scale of a model. I might have also chosen the domain size of the model. What would the difference be between those two? If I non-dimensionalize based on the domain size of the model, what kind of dynamics is that set of equations going to describe? It's going to describe what the model resolution is good for. All of the resolution of the model is being oriented around whatever dynamics are the biggest thing that can fit in the box we're simulating. If I build it instead based on the grid size, I'm talking about the biggest thing I can't resolve. And so doing it this way is orienting us towards what we need to parameterize, the things that are smaller than our model grid when I take the dimensionless equations based on the grid scale. Okay. All right, so how big is the Rossby number? How big? We talked about it already. How big is it for the mesoscale? 0.1. How big is it for the submesoscale? 1. Okay. For the mesoscale, then, I could throw out all those terms. I could neglect them because they're only a 10% correction on that equation. For the submesoscale, I got to keep them. Okay? Froude number, which is the inverse square root of the Froude number squared is basically 1 over the Richardson number. We talked about the Richardson number before. So in the mesoscale, these terms are about a 1% correction to the vertical equation. So we could drop those too. And we see that what's left over is the geostrophic and hydrostatic balance along with some dissipation, which is also small because the Reynolds number is very large for the ocean circulation. So when we talk about geostrophic balance, hydrostatic balance, the ones that we learned in class, they are very appropriate for mesoscale dynamics. And in fact, if you throw this term out and this term out and you make a set of equations out of all of these, the first prognostic equations that come to mind, those are the quasi-geostrophic equations of motion. So that's essentially how you build them. You throw out these guys with the Froude number out front, you throw out these guys with the Rossby number out front. So is that going to be a good approximation for the submesoscale? Certainly not for this one, because now we've got an order 1 number out front. We can't throw out those acceleration terms. We might still get away with throwing this part out and remaining in a hydrostatic model, because even though the Froude number has gone to order 1 for the submesoscale, the grid aspect ratio, our eddies are still 10 kilometers wide and only 100 meters deep. So if we resolve those equally well in the horizontal and the vertical, this is going to be a small number. Okay? So for submesoscale reduced dynamics, we probably can still use the hydrostatic equation instead of the full vertical equation, but we probably should not use the geostrophic balance. Okay? I think that's all I wanted to say here. Okay. So those are the way we think about reduced models, but let's hear something new. Okay, let's talk about another reduced model, which you may, everybody, well, some of you might have, Fabrice knows all about it, the wave average Boussinesq equations. So this is the idea that we're going to filter in time over the period of surface waves and retain only the leading order contributions from the surface waves to the slower motions. Okay, and people have been using that to simulate Langmuir turbulence for about 20 years, but we can do more with them. And what do I mean by that? Once we have an equation set, and it's okay for a particular set of scales, you can always use it at larger scale, no problem. You just need more computer power. So if we could afford to use the Navier-Stokes equations for the globe, they're just fine. The problem is going the other way, that going from big to small, you have to change the equations, or as we drop our resolution, we have to change the equations to handle the coarser and coarser phenomenon. So a reduced model changes the equations of motion in order to bring some faster or smaller dynamics up, and also limit some of the pieces to make it more efficient. Okay, so this simulation that I showed before is actually simulating the wave-averaged Boussinesq equations of motion. And so we got Langmuir cells in there. And here's some Langmuir. Here's the normal explanation for Langmuir cells. So if the wind and waves are going this way, you actually take, if there's a little jet that happens to be there on the surface, then that jet gets tilted over by the Stokes drift of the waves and gets stretched. So the tilting and stretching terms in the vorticity equation spin up these counter-rotating gyres, counter-rotating cells. So this guy has vorticity going down, so we tilt it over, and now it's got vorticity going this way. This guy has vorticity going this way. We tilt it over, and now it's got vorticity going this way. Okay? This is how we write in the wave average equations. And sorry, I just switched to Cartesian tensors on this slide. I hope that's okay with you guys. There's an advection term, which is now the Lagrangian advection. So that includes the Stokes drift. And there's this crazy term, the Stokes shear force term, which is when the Lagrangian velocity and the Stokes drift vertical shear are aligned, there's an extra term. So that's a residual of the wave motion that's coming back into the larger scale motions. So let's think about how that term works a little. Okay, here we go. If we have that same circulation before where we have a little surface jet and the Stokes drift is going in the same direction as the surface jet, this term says, here's the direction of my Lagrangian velocity. Whenever the Lagrangian velocity is in the same direction as the Stokes shear, which it is right here in the middle, you get, this term is positive, downward vertical acceleration. It pushes down in the middle. Okay? Out here, we have a smaller Lagrangian velocity in the direction of the Stokes drift, and so it pushes down just a little, not as much as in the middle. And if you look at those two and you say, hey, what kind of a circulation is that going to drive when I'm pushing down a lot in the middle and a little on the sides? It's going to drive an overturning circulation like that. So this is the way in the vertical momentum equation to understand where the Langmuir cells come from. Okay? So we did the vortex tilting form, and then we did this vertical momentum equation. These are identical. You can reshuffle, you make the vorticity budget out of this vertical momentum equation, you end up getting that tilting explanation. Okay, but there's another reason for that. Oh, why didn't it come yet? You might wonder if including this term in a hydrostatic model was a good idea. So we talked about the hydrostatic approximation being a good approximation for the submesoscale. We don't want to make the geostrophic. We could make the hydrostatic. Do we need this wave term in the hydrostatic approximation? Well, the question is then, do surface gravity waves affect the submesoscale the same way that they do Langmuir circulations? Okay, we can think about that a little. I think I'm going to skip these pieces. I know I'm not going to have time. Sorry. This is all just basic Langmuir stuff. You already saw that figure. And this is more examples of Langmuir stuff. Okay. Let's go back to this movie. Okay. So we've got Langmuir cells. Langmuir cells. And we just learned why they're there. They're there because when the Langmuir cell has a little Lagrangian velocity excursion in the direction of the Stokes drift, it gets a downward force from the Stokes shear force. But what about this front? It's got a big Lagrangian velocity. We know it does because, look, it's moving the temperature. It's got a big Lagrangian velocity that also has a strong projection into the direction of the Stokes drift. It should feel a Stokes shear force impact as well, if this is right. And so remember, that simulation is embedded inside this larger submesoscale domain. So that little box was the box that we just saw. So that front that we just analyzed happens around there at that moment in that simulation. So there is a submesoscale to check out. So we can go into the equations for, these are the wave average Boussinesq equations, which again, as I said, they've got Lagrangian advection, they've got this Stokes shear force, and the other funny thing they have is a Lagrangian Coriolis force. Those are the three pieces. And importantly, how big is this guy, this epsilon that tells us how big that term is versus the buoyancy? When are the surface waves going to have as big of an impact as the buoyancy does on that submesoscale dynamics? That's the question we might have. Okay. I just explained those 3 slides, and I'll skip that one. Okay. Here's a map using WaveWatch to get the wave information, so I get the Stokes drift from that, and using sea surface temperature to infer the buoyancy gradients, and sea surface altimetry to infer the Rossby number, and I'm after finding how big epsilon is, that wave impact versus buoyancy versus the Rossby number. Okay, why am I comparing to Rossby number? One, the Rossby number, remember we said that was the thing that says you are safely mesoscale or submesoscale. When this guy is order 1, that means that you're submesoscale. When that guy is smaller than 1, you're safely mesoscale. So I'm basically asking, are waves more or less important for the submesoscale than the Rossby number? We just said the Rossby number. We can't neglect those horizontal acceleration terms for the submesoscale. Now the question is, can we neglect the wave forcing terms for the vertical equation? Okay. And the other reason why is because there are a few things in here that are hard to estimate, and if I take the ratio, the hard things cancel out. So that's the real reason why I did it. Okay. This goes from 100 in a few weird spots down to 1/4. So in the tropics, we probably should be more worried about the Rossby number, the finite Rossby number effects than the wave effects. But everywhere else, 4s and 10s. That effect of the surface gravity waves affecting the submesoscale is predicted to be more important than finite Rossby number in most of the world. Okay, so this is a reduced model which has a very surprising set of dynamics in it. So if we say we should be wavy hydrostatic rather than hydrostatic for all of the regions where that's greater, most of the world is a wavy hydrostatic region. Okay, so let's think a little bit about what the submesoscale is likely to do. One more slide. Okay, so for the Langmuir cells, we said, hey, we get a downward force wherever we have a Lagrangian current oriented in the direction of the Stokes drift. For the submesoscale, we'll get a downward force everywhere we have a Lagrangian current in the direction of the Stokes force. Just the same mechanism, nothing different, just on a larger scale. So let's look at an example. So the typical effect will be downward force for downflow Stokes. Let's look at an example in that simulation where this happens. Okay, so this is a snapshot from that big simulation of the vertical vorticity near surface in a simulation that includes Stokes drift, and we actually burned all the computer time to run exactly the same simulation with no Stokes drift. So this is the wave average Boussinesq equations. This is the regular old Boussinesq equations without any wave averaging. And you can see there's something qualitatively different about those fronts over there and the kind of sea of fronts over here. And in vertical vorticity, remember when we have a front, we expect to see positive vorticity sitting right next to negative vorticity. So these white next to black stripes each indicate a strong front. The same is true over here. But can anybody see what the difference is between this and this? What's special about the fronts on that side that's not that way on the right side? They're sharper, so they're stronger. And they're also all aligned in almost the same direction as the Stokes drift. They are strongly anisotropic over there. Here, they're kind of every which way. That's not the direction that we initialized the model. They are growing stronger because of the Stokes drift. And so we can make lots of these little 1 kilometer by 1 kilometer boxes all over the place and examine these dynamics. And this one that I keep showing the movie from is our favorite one because it's got such a nice strong front sitting right in the middle. Other ones, whoa, why didn't the movie play? Other ones, the fronts don't align with the wind and they're not as sharp. Okay? And so, if we think about this mechanism again, acting on that front, let's see how it goes. Let's see what the story looks like. Okay, now this is a snapshot where that front is sitting right here. And this is the horizontal velocity oriented in the direction along the front. So you can see there's a big red blob. That's where that front is. And I have this little box drawn on here. This is our analysis window box. We're going to look at the force balances in that little window around that front. And that front is there because there's a temperature gradient. So there's cold stuff on one side and warm stuff on the other side. There's that strong front just blasting away, submesoscale front, so that the velocity anomaly is sitting right on the gradient of the temperature, the way we'd expect. And now here's an interesting thing. This is the vertical velocity field. And out here away from the front, look, there are Langmuir cells everywhere. Langmuir cells, Langmuir cells, Langmuir cells, Langmuir cells. On the front has a big vertical velocity sitting on it. Right along the temperature gradient, there's a big long strip of downward vertical velocity. Okay? And if we release surface drifters in that flow, they all pile up right on top of the front unless they get caught in a Langmuir cell somewhere else. So that front is behaving an awful lot like a Langmuir cell. It's oriented in the same direction as the wave direction. It's got a big downward velocity right in the middle of the front, and it seems to collect drifters the same way that a Langmuir cell does. Now, if we think about the traditional understanding of why fronts are there, there's a secondary process. So the mesoscale eddies strain the temperature together, putting cold next to warm. And then there's an overturning circulation that goes like this. So we're looking from the side. Here's the front, that big gradient in temperature. And we expect there to be an overturning circulation that goes like this and brings together stuff at the surface to converge on that point. That's why it gets there. It sharpens itself. So this is the traditional theory of fronts in the atmosphere, just applied. But we can wonder whether the Stokes shear force has an impact here. And what I would say is, right on the nose of that front, where the Lagrangian velocity is oriented with the Stokes drift, we see there's a big jump downward in the overturning stream function. So the Stokes shear force is making itself felt on the secondary circulation of that front, which is strengthening the front. It only happens when the fronts are aligned with the Stokes drift. If they're going in a different direction, this force doesn't kick in, and it should predict that the strongest fronts are all oriented in the same direction. And the last little piece of work we did was to budget what all the sources are for the vorticity involved in that secondary circulation, that overturning cell. 40, if the normal explanation for why fronts exist is 100, 100%, 45%, so about a third of the effect, a third of the reason for that front to be there is coming from the Stokes shear force. So this is a reduced model that actually changes your mind about how dynamics works. At the submesoscale, because we included the Stokes forces that were coming from averaging over the surface waves, we actually see quantitatively and qualitatively different behavior in the submesoscale dynamics by bringing forward that piece. Okay? So, is that everything we want to know about surface waves? Certainly not. You can think about it affecting ice or mass fluxes or heat fluxes, kinetic. There's a whole zoo of things to think about like this. That's just one example of a story bringing forward by using the right reduced dynamics, being able to see the connection between scales like that. Okay, that's the end of this piece. So, one more last piece. So we said for the Boussinesq system, we lost the ability to study heat engines. We lost the ability to study sea level rise. What do we lose in going to this wave average system over the real system, which just has the gravity waves in there? Well, our waves can't break. We threw away all the terms involving wave breaking. We just kept the Stokes drift. There's a limit on the wavelength of waves versus the scale of the phenomenon that we're studying. We have to keep our resolved dynamics, those fronts had to be bigger than a wavelength of the waves for this to be a appropriate simulation. And we lose everything about the phase of the waves, like freak waves, rogue waves, other kinds of phenomena that depend on waves adding together at one phase to make a bigger or smaller event. And probably lots of other things that I don't even know what they are, because the system hasn't been studied that well. Okay, there we go. So, the equations of motion are known when there's sufficient resolution, but we can only simulate about a teragrid, so we have to make choices. Using reduced models help connect in a dynamically relevant way, in a more efficient way, phenomena across scales. So today we discussed the kinds of science you can do by ignoring waves, sound waves, the Boussinesq, or averaging over waves, which is the wave average Boussinesq equations, and some of the trade-offs. So tomorrow we're going to discuss the other side of this, where we start to build parametrizations, that is, actively re-inject the effects of small-scale phenomena that are not resolved. All right, thanks.
This may be a very stupid question, but do you have any idea what would happen if this wave climate effects would be included locally with unstructured mesh, locally refined? What would happen with the global impact of this wave climate interaction?
So the wave, so the wave submesoscale interaction, or the wave climate interaction. So in both cases, this is a pretty. Let me say. We'll do my favorite trick. We'll go back and stare at the equations and see whether it tells us. Yes, essentially is the answer, but I want to be a little more specific why.
So it should be outside the tropics, right, or what?
Yeah, so outside the tropics in that map, anywhere outside the tropics on some scale, the wave interaction is kicking in. But you might wonder whether the wave interaction kicks in before or after this part. So this part goes with Rossby, and the wave piece, sorry, I didn't show it in this version, comes in here with that epsilon out front. So the purpose of that was to show that actually this one comes in first before this one, but when you have an adjustable mesh, you have to be aware that both this one and the other one depend on horizontal length scale. So they come in increasingly strongly the smaller scale you get, so you probably shouldn't neglect them even when you're too coarse to have them do much.
But then we lose the advantage of the locally refined mesh, no?
No, you'll lose this effect when you get coarse, which is what you won't be able to resolve the interaction, even though the forcing terms are there. They won't be as big as they would be at higher resolution. And in fact, someone checked how big the wave interaction terms were in a climate model just by directly sticking them in the equations, and the answer is not very important. Not because they're not important in the real world, but because the resolution of a climate model is too coarse to have either the Rossby term or the wave interaction term be large.
Thank you.
Sure. Okay.
Thank you very much, Baylor.